Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on oxidation reduction reactions. The first thing we want to talk about today is how to balance redox reactions. This is going to involve us recalling our general rules for balancing chemical equations. I have them listed here. The first thing that you want to do is determine what reaction is occurring. What are the reactants, what are the products, and what are the physical states involved? Once you've figured that out, you can go ahead and write the unbalanced equation. Looking at the unbalanced equation, you're going to balance one atom at a time, starting with the substance that has the most elements present. If necessary in this step, you can use fractional coefficients to balance the simplest substance. But in the fourth step, you're going to want to get rid of those fractional coefficients. So if there are any, multiply each coefficient by a factor that's going to result in the smallest whole number coefficient. Then last but certainly not least, double check that each atom is indeed balanced. Now we have an added consideration here. For redox reactions, to balance them, both the net charge and the number of atoms must be equal on both sides of the equation. Now, by assigning oxidation numbers to the atoms in both the reactants and products, you can identify which atoms are oxidized and which atoms are reduced. Now, this step is essential because it helps to determine how many electrons are lost in oxidation and gained in reduction. Now, the most common method for balancing redox equations is the half reaction method. It's also known as the ion-electron method. In this method, the equation is separated into two half reactions, the oxidation part and the reduction part. Now, each half reaction is then balanced separately, and then they're added together to give a balanced overall reaction. So what we want to do here is go over some of the detailed steps on how to balance redox reactions, and then we're going to jump into a practice problem. In that practice problem, these steps will make more sense. The first thing is you're going to want to identify the oxidation and reduction half reactions. So you're going to separate the overall redox reaction into two half reactions, one that represents oxidation and one that represents reduction. Then you're going to go ahead and you're going to balance each half reaction. You're going to balance atoms other than oxygen and hydrogen first. Then you can balance oxygen atoms and hydrogen atoms. A side note here for balancing the oxygen and hydrogen atoms. In an acidic solution, you can balance oxygen atoms by adding water to the side that is oxygen deficient, and you can balance the hydrogen atoms by adding hydrogen ions. In basic solutions, you can instead use hydroxide and water to balance. Also, you want to balance charge. So you're going to add electrons to one side of the reaction to balance the charge. The number of electrons added should equal the change in oxidation state so that it ensures that the total charge on both sides of the half reaction are equal. The next step is to equalize electron transfer. Multiply each half reaction by a coefficient so that the number of electrons that is lost in the oxidation half reaction equals the numbers of electrons gained in the reduction half reaction. And again, this is going to ensure that electrons are conserved in the overall reaction. Then you're going to combine those half reactions. You're going to add the two half reactions together, and you're going to ensure that electrons cancel out appropriately. You're going to combine the reactants and products to obtain the overall balanced redox reaction. And then, of course, last but not least, you want to verify that everything is indeed balanced. With these rules in mind, let's go ahead and tackle a practice problem. This example wants us to balance the following redox reaction using the half reaction method. What we have here is the permanganate ion reacting with the iodide ion to form molecular iodine and the manganese 2 ion. The first thing that we want to do is assign oxidation numbers so that we can determine the oxidation half reaction and the reduction half reaction. Let's start with our permanganate ion. The most electronegative element here is going to be oxygen. It's going to have an oxidation number of -2, and there are a total of 4 oxygen atoms, so we have a total of -8. Now, something that's important to keep in mind is that the sum of the oxidation numbers of the atoms that are present in a polyatomic ion, like permanganate, is going to be equal to the charge of the ion. Here, that's going to be -1. In that case, the manganese is going to have an oxidation number of +7, because +7 minus 8 gives us a total of -1, and that matches the charge of the ion. The next one we want to work on is our iodide ion. What is the oxidation number here? Well, what we have is a monatomic ion. The oxidation number for a monatomic ion is going to be equal to the charge of the ion. So the oxidation number here is going to be equal to -1, just like the charge of this iodide ion. Next up, we have molecular iodine. The oxidation number here is going to be 0. Remember, the oxidation number of a free element is 0, always. Last, we have our manganese 2 ion. Again, this is a monatomic ion, so the oxidation number is equal to the charge of the ion, which in this case is going to be +2. Now, the next thing we can do is figure out what our oxidation half reaction is and what our reduction half reaction is. Let's go ahead and take a look at our iodide ion and compare it to molecular iodine. Here, the iodine atom goes from -1 oxidation number to 0. It is losing electrons. So this is our oxidation half reaction. I'm going to go ahead and write it right here. Now, what about our reduction half reaction? Let's take a look at our permanganate ion and compare it to our manganese 2 ion. Here, manganese goes from +7 oxidation number to +2. It is gaining electrons. So this is our reduction half reaction. Now that we have that figured out, our next step is to go ahead and balance these half reactions. We're going to start with our oxidation half reaction. Now, this oxidation half reaction involves iodide ions transforming into molecular iodine. Here we have 2 iodine atoms. Here we have 1. To balance that, we're going to add a coefficient of 2 here. Now that we have these atoms balanced, the only thing we're concerned with is also balancing the charges by adding electrons where they're needed. The charge on the reactant side is -2 because we have 2 iodide ions, and the charge on the product side is 0. To balance this, we're going to add 2 electrons to the product side. Now, our oxidation half reaction is all good and balanced. We can go ahead and move into our reduction half reaction. Now, here, we're going to first balance the manganese atoms. Since one manganese atom is present on both sides, it's already balanced. So then we move on to balancing the oxygen atoms. All right, and we're going to do this by adding water. On the reactant side, we have 4 oxygen atoms. So I'm going to go ahead and add 4 water molecules to the product side so that we now have 4 oxygen atoms on the reactant side, 4 oxygen atoms on the product side. Then we're going to balance the hydrogen atoms. On the product side, we have a total of 8 hydrogen atoms. So we're going to want to add 8 hydrogen ions to the reactant side to make sure that now our hydrogen atoms are balanced. Then finally, we want to balance the charges by adding electrons. Let's look at our reactant side. Here we have a -1 charge, and then we have 8+ charge from our hydrogen ions. This gives us a total charge for our reactant side of +7. On the product side, we only have a charge of +2 from that manganese 2 ion. The only way that we can balance these charges is if we add 5 electrons to our reactant side. When we do that, we now have a total charge of +2 in the reactant side that perfectly matches our +2 charge on the product side. Now that we have balanced these reactions, we want to combine them back together. To combine the half reactions, we have to ensure that the number of electrons lost in oxidation equals the number of electrons gained in reduction. So here for our oxidation half reaction, we have a total of 2 electrons on the product side. And in our reduction half reaction, we have a total of 5 electrons on the reactant side. This is good. They're on opposite sides so that when we add this together, they're going to cancel each other out. But the problem is we have 2 and 5. Those aren't going to properly cancel each other out. What we're going to do is multiply each half reaction by the appropriate coefficient that's going to get us to have an equal number of electrons on both sides. That means I'm going to multiply the oxidation half reaction by 5, and I'm going to multiply the reduction half reaction by 2. This is going to give us the following oxidation half reaction now that we've multiplied it by a coefficient of 5. And we're going to get the following reduction half reaction now that we've multiplied it by a coefficient of 2. And now that we have matching number of electrons, one on the product side, one on the reactant side, when we add these together, they're going to cancel each other out. And that is exactly what you want. Now we can go ahead and write the overall reaction. Adding these balanced half reactions together gives us 10 iodide ions plus 2 permanganate ions plus 16 hydrogen ions. And that gives us on the product side 5 molecular iodine molecules plus 2 manganese 2 ions plus 8 water molecules. And there you have it. We have now solved this problem. Let's go ahead and move into our final conversation before we move into our last and final objective. To conclude this section, it's important to revisit and clarify the terminology that we used for oxidation, reduction, and their corresponding agents. The phrasing, it may vary slightly across different classes or textbooks, but the underlying concepts remain the same. For oxidation, oxidation refers to the loss of electrons. That is the all-purpose definition. In general chemistry, oxidation is characterized by an increase in the oxidation state of an element. In organic chemistry, oxidation is often associated with the gain of oxygen or the loss of hydrogen. For instance, when a molecule loses hydrogen atoms or gains oxygen atoms, it is said to be oxidized. For reduction, the all-purpose definition is that you gain electrons. It is the gain of electrons. In general chemistry, reduction is the process that is marked by a decrease in the oxidation state. In organic chemistry, reduction usually involves the loss of oxygen or the gain of hydrogen. Now, the substances that facilitate these processes are known as oxidizing and reducing agents. An oxidizing agent causes another substance to be oxidized. Chemically, it is the substance that is reduced because it gains the electrons lost by the oxidized substance. For an oxidizing agent to function, it must contain an element in one of its higher oxidation states and ready to accept electrons. On the other hand, reducing agent causes another substance to be reduced. It is the substance that is oxidized in the reaction as it donates electrons to the substance being reduced. A reducing agent must contain an element in one of its lower oxidation states, and it's supposed to be prepared to lose electrons. Now we can move into our final objective. Here, we're going to revisit the topic of net ionic equations. We have discussed net ionic equations plenty of times in this playlist, and we've discussed the three main steps to writing our net ionic equation. The first step, you want to write the molecular equation. You want to write the reactants and the products in their undissociated form. Then in the second step, the total ionic equation, you want to write your aqueous reactants and products in their dissociated form, keeping in mind that our solids, our insoluble salts, are going to stay as is. Then you're going to get rid of your spectator ions. These are the ions that appear in both the reactant side and the product side. You're going to get rid of those, and what you will be left with is your net ionic equation. Now, a common example we have gone over several times is the reaction between silver nitrate and sodium chloride. So here is the reaction in its undissociated form. Here is the total ionic equation where we write our aqueous solutions in their dissociated form. And once we get rid of the spectator ions, which are our sodium ions and our nitrate ions, we are left with the net ionic equation. Now, in chapter 4, we discussed reaction types. And when we did, we left out the rationale for why certain elements come together and others do not. Now that we have discussed oxidation reduction reactions, it should be more clear that the gain and loss of electrons drives the formation of many compounds, especially ionic ones. So what we're going to do now is we're going to revisit many important reaction types and understand their basis in oxidation reduction reactions. Let's go ahead and get started with combination reactions. Combination reactions are when two or more species come together to form a product. Now, in this reaction, we have hydrogen and fluorine gas combine to form hydrogen fluoride. To understand this reaction, we can go ahead and break it into two half reactions that separately show the oxidation and reduction processes. Here is our oxidation half reaction. In this half reaction, we have molecular hydrogen. It loses electrons, indicating that it is oxidized. Each hydrogen atom here goes from an oxidation state of 0 to an oxidation state of +1. Notice that here we've added 2 hydrogen ions so that we can balance our hydrogen gas. And to balance the charge, we've also added 2 electrons. Here we see our reduction half reaction. In this half reaction, molecular fluorine gains electrons, indicating that it is reduced. Each fluorine atom in F2 goes from an oxidation state of 0 to -1. And to the reactant side, we've added 2 electrons to balance the -2 charge on the product side. Now we can combine the 2 half reactions to get an overall balanced redox reaction. This is our overall balanced redox reaction, and it shows the transfer of electrons from hydrogen to fluorine. Now here, hydrogen acts as a reducing agent because it donates electrons and it is oxidized from an oxidation state of 0 to +1. Fluorine here acts as an oxidizing agent because it accepts electrons and it is reduced from an oxidation state of 0 to -1. Now, in this reaction, there are no spectator ions because all of the species are actively participating in the redox process. And the entire process involves the direct transfer of electrons from hydrogen to fluorine, resulting in the formation of hydrogen fluoride. Now that we've talked about combination reactions, let's talk about decomposition reactions. This is where one product breaks down into two or more species. Here we're going to look at the decomposition of ammonium dichromate. Let's go ahead and write the half reactions. What you see here is the oxidation half reaction. In this half reaction, the ammonium ion loses electrons, indicating oxidation. The nitrogen atoms in the ammonium ion, they have an oxidation state of -3, which changes to 0 in nitrogen gas. And here we've added 8 hydrogen ions to the product side to make sure that the hydrogen atoms are balanced and that the charge is also balanced. Here you see the reduction half reaction. So in this half reaction, the dichromate ion gains electrons, indicating reduction. The chromium atoms in dichromate ion have an oxidation state of +6, which changes to +3 in chromium 3 oxide. Now we can go ahead and combine the two half reactions, and we're going to get the following overall balanced redox reaction. Now the nitrogen atom in the ammonium atom, or in the ammonium ion, acts as a reducing agent because it donates electrons and it's oxidized from an oxidation state of -3 to 0. Now the chromium atom in the dichromate ion acts as an oxidizing agent because it accepts electrons and it is reduced from an oxidation state of +6 to +3. Now in this reaction, there are no spectator ions because all of the ions here are actively participating in the redox process. The nitrogen from the ammonium ion is oxidized, and the chromium from the dichromate ion is reduced, and the result is the formation of nitrogen gas, chromium 3 oxide, and water. Let's go ahead and talk about combustion reactions next. Combustion reactions, these are described as a fuel, usually a hydrocarbon, that's mixed with oxygen, and it forms carbon dioxide and water. So our example reaction here involves methane and oxygen gas. They react together to give us carbon dioxide and water. And we can go ahead and write the half reactions. Here you see the oxidation half reaction. In this half reaction, carbon in methane, all right, the carbon in methane loses electrons, indicating oxidation. So the carbon atom in methane, it has an oxidation state of -4, which changes to +4 in carbon dioxide. Now we can look at the reduction half reaction as well. In this half reaction, oxygen molecules gain electrons, indicating reduction. Each oxygen atom in oxygen gas has an oxidation state of 0, which changes to -2 in water. And here we use water to balance the oxygen atoms. And we also have 8 electrons here in the reactant side to balance charge. We balance charge with these 8 hydrogen ions that we've added to the reactant side to be balanced with the 8 hydrogens we have from water on the product side. And similarly, going back to our oxidation half reaction, here we have 8 electrons to balance the charge as well. Now, we can go ahead and write our overall balanced equation. All right, we can go ahead and write our balanced overall equation, and we get the following equation, there are no spectator ions here. Now, the carbon atom in methane, again, acts as the reducing agent because it donates electrons and it is oxidized from an oxidation state of -4 to +4. The oxygen molecule acts as the oxidizing agent because it accepts electrons and it's reduced from an oxidation state of 0 to -2. Now, combustion reactions, they often have complex half reactions depending on the type of fuel used. You can see it here as well. It's pretty complex and it's a lot more species involved than some of the other reaction types we've looked at. In this instance, the carbon in methane is oxidized and the oxygen is reduced. Wonderful. Let's move on to the next reaction type, double displacement reactions. Double displacement reactions involve the switching of counter ions. Now, because all ions generally retain their oxidation state, these are not usually redox reactions. So, for example, in this reaction between silver nitrate and hydrochloric acid, we form nitric acid and silver chloride. Again, in this double displacement reaction, there's no change in oxidation states. So the net ionic equation really just highlights the formation of the precipitate without altering the charges of the ions. And so in this net ionic equation, we have silver ions and chloride ions combined to form solid silver chloride, demonstrating that exchange of ions. Now, the remaining ions, hydrogen ion, nitrate ion, they stay in solution as spectator ions, and they're not involved in the formation of the precipitate. Now, next up, we want to talk about disproportionation reactions. This is a specific type of redox reaction where a single element undergoes both oxidation and reduction within the same reaction, and it results in two different products. This type of reaction is actually quite common in biological systems, and it's utilized by many enzymes. An example is catalase. Catalase helps protect cells from oxidative damage by breaking down hydrogen peroxide, which is a potentially harmful byproduct of metabolic processes. So the reaction for that is two hydrogen peroxide molecules break down to two water molecules and oxygen gas. Now, in hydrogen peroxide, the oxidation state of each oxygen atom is -1, and the oxidation state of the hydrogen is +1. There's two of each, and that gives us a perfect neutral compound when we sum up the oxidation numbers. Then in water, the oxidation state of oxygen is actually -2. All right. And in molecular oxygen, the oxidation number for oxygen is 0. So one of the oxygen atoms in hydrogen peroxide is oxidized from an oxidation state of -1 to 0, forming oxygen gas. This means it loses electrons and it's been oxidized. And then the other oxygen atom in hydrogen peroxide, it's reduced from an oxidation state of -1 to -2, forming water. So this means it gains electrons. So in this single reaction, oxygen undergoes both oxidation and reduction, and this is the definition of a disproportionation reaction. Lastly, let's briefly cover oxidation reduction titrations. These are a type of titration that's used to determine the concentration of an unknown solution through a redox reaction. So very similar in setup to acid-base titrations. Redox titrations just involve the transfer of electrons instead of protons. The goal is to reach the equivalence point where the amount of titrant added is stoichiometrically equivalent to the quantity of the analyte in the solution. Indicators that change color at specific voltage values can then be used to signal the equivalence point in redox titrations. Now, quickly, there are two types of redox titrations I just want to quickly define. First type is ideometric titrations. These involve the use of iodine as the titrant. Iodine can act as both an oxidizing and reducing agent, and this method is particularly useful for determining the concentration of substances that can oxidize iodide ions to iodine or reduce iodine to iodide ions. And the endpoint is usually detected by a starch indicator, which forms a blue-black complex with iodine. Then we have potentiometric titration. This is a method where no chemical indicator is used. Instead, the progress of the titration is monitored by measuring the electrical potential difference, the voltage of the solution, with a voltmeter. And as the titration progresses, the voltage changes, and this change is used to determine the equivalence point. So this is analogous to following an acid-base titration with a pH meter instead of a color indicator. And they are highly accurate, and they're often used when precise determination of an endpoint is required. So with that, we've completed all our topics for this chapter. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.